This video covers basic aspects of relativistic mechanics. Relativistic mechanics provides a description of a systems where the velocities of moving objects are comparable to the speed of light. Imagine two inertial frames for two observers. The first is denoted xt and the other x prime t prime. The second is moving in relation to the first with a velocity vr. Imagine an object that is moving in xt with velocity v. In Galilean relativity, the velocity of the object or particle in the x prime t prime frame of reference is. What we will address now is how to determine the velocity v prime from v and vr in special relativity. Special relativity transformation equations are taking the differentials of the equations for x prime and t prime yields, dividing the equation for dx prime by the equation for dt prime we obtain, or which can be rearranged as or. And finally, the inverse equation is. Those are the special relativity equations for velocity addition. Let's see how accelerations are converted from the stationary frame of reference to the moving frame of reference. Let's start with the velocity composition equation for special relativity, which can be written as taking the derivative with respect to time t we obtain. But we have taking the derivative with respect to time t we obtain. So we can write or substituting the second equation in the first one we obtain or, which simplifies to. Since accelerations depend on the frame of reference, forces will also depend on the frame of reference. Newtonian mechanics needs to be modified to relativistic mechanics. We will now discuss an interesting outcome of special relativity. To understand it, we need to use relativity equations in two spatial dimensions. In special relativity, length contraction only occurs in the direction of the relative movement. We will assume that the two frames s and s prime are moving with a relative velocity vr in relation to each other in the x direction. The other Cartesian spatial direction is denoted y in frame s, and y prime in frame s prime. The special relative transformation equations using two spatial coordinates are. The velocity transformations are. So although the coordinates in the y direction are not affected by relative movement in the x direction, this movement requires a transformation equation for velocity in the y direction. For the accelerations we have. Even when there is no force acting on a particle in the y direction in frame s, and therefore no acceleration, in frame s prime there is acceleration in the direction y prime caused by the relative movement in the x direction. This is in essence what is behind the static electrostatic force and the magnetic force for particles moving in electromagnetic field. In classical mechanics, electrostatic and magnetic forces are two different forces. In special relativity, they are two different components of the electromagnetic force. Imagine two inertial frames. The first, s, is based on x and t coordinates, and the other s prime, is based on x prime and t prime coordinates. The frame s prime is moving in relation to frame s with a velocity vr. Consider a particle p at rest on frame x prime t prime. At a time of 0, the particle p splits into two smaller particles a and b. An observer using s prime as his proper frame measures the velocity of the split particles as minus vr and vr respectively. What we know from the statement is, we would like to determine the relationship between the particle masses, the velocities as measured from frame S and the linear momentum expressions in S and S prime frames of reference. We will assume that the mass as perceived by both frames of reference may be different. So mass conservation becomes the special relativity velocity transformation equation is. So in frame S the particle p velocity is, and the velocity of particle A is, and for particle B we have linear momentum before the split in frame S is written as and after the split it is written as linear momentum before the split in frame S prime is written as and after the split it is written as the linear momentum conservation equation in frame S prime yields the linear momentum conservation equation in frame S yields. But we have. So the linear momentum can be written two ways in frame S. Or we will use those two versions of the conservation of momentum equation in frame S to substitute the relativity velocity with particle B velocity. Squaring the second equation and dividing the result by c square we obtain dividing one equation by the other we can eliminate VR. So we obtain which can be simplified to and finally in special relativity, mass needs to be a function of velocity to conserve momentum. We can define mass as a function of the particle velocity and its rest mass m0. For particle A we have from the equation for mass mb it is clear that particle B has the same rest mass as particle A. So, the total mass for the original particle is and the rest mass of the particle before split is in S prime we have for particle A and for particle B we have and for the original particle before the split we have. Finally, the linear momentum can be written as. More recently physicists have dropped the notion of relativistic mass, stating that the mass is always the rest mass, and the above equation is the correct expression for relativistic momentum. Force is defined as the rate of change of linear momentum with time. The work done by a force is equal to the change in kinetic energy. The change in kinetic energy can be written as or finally, integrating by parts we obtain or which becomes using the limits of integration we obtain which can be further simplified to, which can be rewritten as, and defining E as, we finally obtain even when the particle is at rest, we have a rest energy E, which is Einstein's famous equation. The mass-energy equivalence in physics states that mass and energy in a system's rest frame differ only by a multiplicative constant and the units of measurement. In a reference frame where the particle is moving, its relativistic energy and relativistic mass obey the same formula. Finally, we can examine the relationship between relativistic energy and momentum. The relativistic momentum is, which can be transformed into and rewritten as, the Lorentz factor is. Using this in the previous equation yields, which simplifies to, but we have, therefore, or rearranging terms. In Newtonian mechanics, the movement of an object or particle is a function of time and is determined if its mass and forces acting upon it are known. All interactions between objects and particles are based on the fundamental forces of nature, that is gravitational, electromagnetic, strong, and weak nuclear forces. All those forces are conservative forces and can be defined by an energy potential field. We will now present a heuristic justification for Lagrangian mechanics without going through a rigorous derivation. The purpose is to obtain a version of Newton's second law for conservative forces that is easier to work with in special relativity. We will concentrate on only one spatial direction. Newton's second law states that the force potential is defined as, the kinetic energy is defined as, our objective is to find a formulation in terms of Newton's second law using the variables position and velocity instead of position and time. Taking the partial derivative with respect to velocity we obtain. Taking the derivative with respect to time we obtain. The force and potential energy potential are linked by the following equation. So Newton's second law can be written as, there is a clear dynamic process between the kinetic and potential energy, which allows us to describe motion using them instead of Newton's second law. This is the beauty of Lagrangian mechanics. Everything is described simply by changes in energy. Apparently, this is a much better approach to special relativity than Newtonian mechanics. But the kinetic energy does not depend on position x, and since potential energy does not depend on velocity, we can write, defining the Lagrangian as, we can write, and the four statements are equivalent.